Good morning and welcome to this webinar, which has been organised by the Construction and Building Services Division in collaboration with the Process Division of the Institute of Mechanical Engineers. My name is Frank Mills. I am Chairman of the Construction and Building Services Division. And our subject today is rising sea levels, which is extremely topical and is the most serious climate change issue facing humanity, not only here in the UK but across the world. More frequent flooding is evident almost everywhere, across the UK, across Europe and across the world. Even inland, where the increased rainfalls resulting from warmer oceans is delivering greater rainfall. And today, we at the institution have published our report on rising sea levels, which is now available on the IMechE website. Today, we have two specialists to present on this subject. John Englander is President of the Rising Seas Institute, and Dr. Tim Fox is Chair of our Process Division of the institution. I would like to hand over now to John Englander to present.
Thank you. It's a pleasure to work with IMechE to understand the impact of rising sea levels on construction and engineering infrastructure and process plan installations. We've been working on this for about a year now, and this is really an advent forward. I'm going to give the kind of content about sea level rise and the framing of why it is unstoppable and unpredictable, and then of course turn it over to my colleagues who can talk about it from an engineering standpoint. We are now in an era where multi-meter sea level rise is likely this century. That's something quite new in all of human civilization. Surprisingly, the process rate is quite unpredictable, and that's a bit counterintuitive, and we'll look at why, which relates to the situation in Greenland and Antarctica with the glaciers. Reducing greenhouse gases could slow the rate of rise, and a lot of effort is going into that. But surprisingly, that reducing greenhouse gases can no longer stop sea level rise. It is unstoppable for centuries. So that's really a fundamental point that we want to take away from this webinar. Sea level rise is headed, I say headed, not going to get there necessarily, but headed to the last high water mark, which was 8 meters higher, some 25 feet, 120,000 years ago. Hopefully we can prevent that from happening, but that was a natural event, so that really gives us kind of a benchmark. To put this in context, we've all seen pictures of the Arctic melting and concerns about polar bears and so on, but the Arctic sea ice does not directly affect sea level rise, surprisingly, and that's a key point to take away here today, is that if ice is floating, either as an iceberg or pack ice, as shown here with the polar bear, or even the ice shelves, the weight is supported on water, and as that ice melts, it does not directly affect sea level rise. Of course, we've seen various depictions of how the world is warmer. This is showing the year 2018 versus the last century's average, and the red, which is 2 degrees Celsius up to 4 degrees, is mostly in the Arctic, and that stems from the spin of the Earth, the Coriolis effect, the placement of the continents, the ocean currents, the tilt of the Earth, all tend to bring the heat to the Arctic, which is where we're seeing the results fastest. If we look at the historical sea level rise, since tide gauges were instituted in about 1850, so 170 years, the rise of sea level is quite clear. It's been a little bumpy, if you will, but a fairly straight line. But in fact, the line isn't straight. It has an upward curvature. And if we look to the satellite data shown here by that little red line for the years since 1992, when the first satellites capable of measuring sea level were put in orbit, that gives us a much more detailed record. And if we look at that era of satellite sea level, which is far more precise than the historic tide gauges, an interesting trend becomes clear. In the first 7 years, the rate was 1.5 millimeters a year averaged. In the next 11 years or so, it was more than double that 1.5 millimeters. It reached 3.2 millimeters a year. And since that period of 2011, roughly, you can see another kind of segment to the arc of the acceleration, and we're at 5 millimeters a year, almost a doubling of the 3 millimeters in the middle segment. So we're beginning to see a doubling trend, and in fact, it's the beginnings of what we are quite certain will be exponential growth. That's hard to see on a year-to-year basis. Most people, not necessarily engineers, but some of your members, but most people around the world assume that the melting icebergs add to sea level rise. And I like to remind people that just like ice cubes in a glass, icebergs float about 10% above the surface because ice is about 9% less dense than water. So if it's freshwater iceberg on saltwater ocean, it's even a little bit higher, but roughly 10% of an iceberg, we all accept that most of it's underwater. We're seeing the tip of the iceberg, as it were. But the corollary of that is that as the icebergs melt, they don't raise sea level because the ice becomes the denser water form again. And so counterintuitively, melting icebergs have no effect on sea level. It's the melting ice on land, the glaciers, that are breaking off and calving into a new iceberg. That's what has the effect to raise sea level, like adding another ice cube to a glass of water. Also, the meltwater coming from the glaciers on land, either on the surface as visible meltwater or beneath the glacier, which is where most of it is actually entering the ocean, that adds to the level of ocean, just like pouring more water in a glass. And the third reason that global sea level is rising is the thermal expansion of seawater. Because the oceans are now about 1 degree Celsius warmer than they were a century ago, they've actually expanded somewhat, about 8 or 10 centimeters over the last century, just from thermal expansion of seawater. So those are the three primary reasons for global changes in sea level. We'll talk about localized issues separately in a moment. Just to visualize a glacier, because it, I think, puts it in quite clear perspective, not only as the glacier comes to the face of the sea and breaks off, is that when we add the iceberg or like a giant ice cube raising sea level. But you can also see here in this photographic image that the ice is no longer white with high reflectance. For different reasons, the ice in the Arctic is becoming quite gray. It's both pulverized rock dust, it's certain algae that are growing, and it's also the deposition of carbon as soot from all the soot that's up in the atmosphere. So the darker face of the glaciers actually absorbs more heat and therefore accelerates the warming process. The Arctic Ocean melting, going from bright white to dark blue, does accelerate the heating as well, because just like a white roof compared to a dark blue roof or car would absorb more heat, that's intuitively accelerates the warming. Local sea level varies because of vertical land movement, which can either be subsidence where the land is moving down or uplift. So let's just cover that. Subsidence can happen because, like shown in the picture of Venice here, the land is literally sinking into the ground. It could be because of it's in a delta area. It could be because of tectonic plates moving. There can be different reasons why land, certain places like Jakarta and New Orleans and Venice have high subsidence. There's places in the world, particularly the northern latitudes from Scandinavia to Alaska, where the land is uplifting. It's actually rising faster than sea level is rising. So sea level appears to be falling in those places. And the reason is because in the far north is where the great ice sheets retreated last, and the decreased weight from those giant ice sheets is causing what we call isostatic rebound or glacial rebound, where the land is moving upwards at a few centimeters. So that's one reason why there's local change different than global change. Also, changing ocean currents will have an effect on relative ocean height. And then something called global mass redistribution. As Antarctica and Greenland melt greatly in the coming decades, as their mass is redistributed around the Earth, it will have a relative effect that the ocean will rise differentially. And it's a little complicated for this purpose, but just the point is that you can't assume that 10 centimeters of global sea level rise will affect every place equally. So a more in-depth study needs to be done for particular locations where we might do the engineering adaptations. I like to suggest that climate change, which is taught as a problem, should be broken into three separate issues. The forcing factor, which is the energy, the greenhouse gases, how we convert from fossil fuels that are making the problem worse. And a lot of effort goes into that in terms of the building's energy efficiency or our power production systems. And that's very critical to reduce the warming. Then in the orange circle there, I show direct effects, from effects on water supply, weather changes, we're getting strange storm patterns, high temperature days, of course, more wildfires, ecological impacts, disease issues, even food supply, will all be effects of changing climate. And then sea level rise is an effect, but it's quite particular because as the ocean rises, it changes the coastline. And that's really the cause of or the focus of our webinar today, to think through how does this impact engineers in their designs and structures moving forward. So we need to have three separate responses to those three separate issues. We need to reduce the warming caused by the increased greenhouse gases. That's often thought of as a sustainability issue. We need to prepare for events like short duration floods. That would be resiliency in my terminology. And then we need to engineer for a new normal like higher sea level, which won't go down for millennia. That would be adaptation. Flooding is often described as a problem, but I like to suggest that we break flooding into 5 different factors: storms, rain, runoff, king tides, and then sea level rise. Also, erosion is often thrown in, and erosion certainly is related to flooding, but it's different than actual water height changes. Erosion is more from storms eating away at the coastline. If we look at the history of sea level since the last ice age 20,000 years ago, we can see that it rose rather dramatically, but it reached the present height about 5,000 or 6,000 years ago. And we have trouble believing that, but if we remember the Ice Age movie, just a bit of humor, but also to remind us that the 2 miles or 3 kilometers of ice, roughly 10,000 feet in the background, as that melted, that's what raised sea level about 120 meters. This chart is something I've put together with the help of many scientists, and it shows 400,000 years from left to right of a greenhouse gas, carbon dioxide in green, the global average temperature in red, and sea level. And we can see that the peaks line up. There is a correlation. The natural ice age cycles between 95 and 125,000 years is driven by an orbital variation called the Milankovitch cycles. We call them roughly 100,000 years, and we're at the normal high spot. We would have been entering the cooling phase when sea levels would have fallen as the glaciers expanded. But in fact, the problem is that these 3 lines all move in parallel, synchronization, if you will. And if we look in the upper right, greenhouse gas, carbon dioxide in particular, is now at 410 parts per million. That's 40% higher than the natural upper bound of 280 parts per million. Carbon dioxide for millions of years has vacillated between the 180 to 280 range, and now we're at 410, and temperatures are warming and sea levels rising as the ice melts. That's the big picture, if you will. We can look to the UK and Europe and see how land masses changed with changing sea level over time. Quite clearly, this is the Dogger Bank. And also Florida is an easy place to see effect because it's a peninsula and relatively low. And if we look at the change from 20,000 years ago when there was ice covering the northern hemisphere to the period 120,000 years ago when the world was in the last warm spot and sea level was 25 feet higher, we can see just how dramatically landforms can change size. The problem for sea level is Antarctica and Greenland. Combined, they hold 212 feet of sea level, about 65 meters. Hopefully, we can prevent them from all melting. Antarctica is melting quicker and quicker, 3 times as fast as just a decade ago. The ice sheets or ice shelves that we see in Antarctica, as shown here, this one's about 100 meters over the surface. About 40 meters over the surface, about 100 feet, but it's 9 times deeper, just like an iceberg. It's floating on water. as this ice shelf breaks off into icebergs, that does not directly affect sea level, but as that bay opens up, way back in the distance there, we can see some mountains on Antarctica. And as the ice shelf clears out of the bay, glaciers will slide from the mountains into the bay, and that's like adding more ice and does raise sea level. These glaciers are being undercut by even the cold water is very effective at eating away at the glacier. Greenland is accelerating faster. It's up there in the northern hemisphere, which is warmer. Greenland is huge, as shown here in comparison to the eastern United States for scale. When we look on top of the Greenland Ice Sheet, I was there a month ago, and I take fact-finding trips there. The clarity that we see thousands of these meltwater streams, as shown here, carrying the water to the ocean one way or another, becomes quite dramatic, really. And then, of course, spawning these enormous icebergs. This was photographed in September 2019, right off Ilulissat, the town in Greenland. So what are the projections for sea level rise? To turn this over to the engineering side here in transition, I use this chart from the Miami region. The 4 counties of South Florida have a shared vision for what they should plan for. And it's interesting that they cite 3 different columns here, from the IPCC to the U.S. Army Corps of Engineers to NOAA. So 3 different agencies, one of them international, of course, the IPCC, part of the United Nations, looking at climate change. And each of them gives a different perspective on sea level projections. And the reason is because they're asking different questions. The scientists are asking, what do we know for certain? And then they recognize they can't predict how quickly Antarctica will melt. The U.S. Army Corps of Engineers designing structures, they take a more cautious approach, talking about taking into account the uncertainty of the melting of Antarctica and Greenland, so their projections are higher. NOAA, which is looking more at short-term weather forecasts, but also is looked to for sea level data, in fact, is taking an even more aggressive approach. If you look at that column, the pink column there. So it's just an example that there's no right number, because it depends on how we want to plug in the melting of Antarctica and Greenland, which are a bit difficult to predict precisely beyond a decade or two. So we often ask how high the water will rise. I like to say the question probably should be, how high could the water rise? It's a very different question. It's like saying, when will the next San Francisco earthquake occur versus when could it occur? An entirely different question and answer. And we need to begin thinking about how high sea level would rise. So I bring this all together, and to turn it over to my colleagues, that looking at what I call a 9-box matrix, if we look out 30 years, 50 years, and 100 years, and you can choose your columns differently, to areas that are low risk, medium risk, or high critical sensitivity to flooding, if we combine all of the inputs and the possibilities and round upward for a margin of safety, we'd come to design criteria from 1 foot up to 20 feet, or 30 centimeters up to 6 meters. And I recommend that IMechE, in fact, use this kind of a simplified set of guidelines that allow people to build and design with a margin of safety. It's an extremely simple graph because, again, it's erring on the high side, and it's looking at what could happen, not what necessarily will happen because of the uncertainty. More information is available in my book, High Tide on Main Street, and I have another book coming out in 2020, Moving to Higher Ground. These are contacts for me if anybody would like to do more research or be in touch about specifics. Thank you.
Thank you very much, John. That provided a really good overview of the context for the rest of our discussion in this webinar today. My role as chair of the IMechE Process Industries Division Board, and indeed the lead author of our recently published report on this topic, is to guide you through an initial engineering response to the challenges that John has just raised. So I'm going to spend the next 20 minutes looking at the detail of the engineering challenge, to present the engineering challenge to you as fellow engineers. I'm going to then explore the IMechE project that we put in place to do an initial scoping of what our professional response to this challenge might look like, provide a bit of information about the project's findings, and then talk a little bit about how we can design in this uncertain world. There's an awful lot of work for us as engineers to do in terms of meeting this new paradigm for us in engineering. But I'm going to give you some initial thoughts from the Institution of Mechanical Engineers as to how we might think about that, and a few points towards the end on what we need to do. So just picking up on where John left off, for us as engineers, we of course have been very used to considering sea level as a relatively fixed component in our design processes and methodologies. So for about the last 5,000 years, as we saw from John's slides, the sea level has to human society, to all intents and purposes, appeared to be stable. And during that period of time, in parallel with that, we've seen the development of engineering as the basis of modern civilized societies. So, of course, any change in that, in particular rapid change in sea levels, potentially present engineers with a significant shift in one of our fundamental design baselines. So that's the position of the coastal shoreline and the heights to which we might expect the water to rise during any natural event associated with the sea. So something that we've taken for granted for 5,000 years from the work that John and others have done appears to be presenting us with a really significant challenge. And the challenge is essentially rooted in instability. So one of the things that we've learned from John's part of the talk today is that there's a lot of uncertainty around what degree and what rate of sea level rise we might expect. So we've heard that the United Nations Intergovernmental Panel on Climate Change's latest projections estimate a maximum of around 1.1 meters of sea level rise by the end of the century. But as we've heard from John, that largely omits the melting of the land-based glaciers in Antarctica. And the National Oceanographic and Atmospheric Administration of the United States has suggested that 2.7 meters of sea level rise might be plausible by 2100. Now, the challenge for us is that engineering buildings and infrastructure typically have a design life of some 25 to 60 years, depending on what the form and function of the building is. And they can often, in fact, be in service for much longer, with life extensions and refits and refurbishments. Some buildings and infrastructure can go on for 100 years or indeed more. We can just think of things like the tube system in London, the railway many of the railway systems in the world, and much of the infrastructure that underpins our urban and industrial environments. So to see sea level change and the position of the shoreline and the heights to which tides rise and various natural events associated with weather impact on our designs as a result of this instability and uncertainty in Antarctica and Greenland warrants a completely new perspective from us as engineers. So the question is, how should engineering respond? This is a question we asked ourselves at the Institution of Mechanical Engineers just over a year and a half ago. And myself and Frank Mills, who is the chair of the Building and Construction Services Division, looked to put together an IMechE project that would scope the degree of this challenge and consider the things that we need to take into account as engineers. So the project involved doing a series of evidence-gathering activities, including one-to-one consultations and facilitated brainstorming workshops, both in the UK and India, We wanted to have an international dimension, and in particular, we wanted a dimension from a developing economy of the world, where the challenges of sea level rise have a different relationship with government policy to maybe those in a mature, developed economy like the UK. And the outcome of the report of the project is to take the findings and to disseminate them into a technical report that we have in fact recently launched. And this provides recommendations for profession, governments, and broader society. And then onwards, beyond this webinar, we'll be disseminating the information to IMechEs and the wider engineering profession. So this webinar is very much a part of that dissemination activity. So the starting point is, how would the world look with a minimum of a 1 meter rise of global mean sea level rise? Well, we chose that figure because that's the high end of the IPCC's predictions, and we wanted to consider first what the basic bottom line baseline criteria for design might look like in terms of the position of the shoreline. So this graphic here shows the sort of changes that we might see across one or two major parts of the world. But of course, as John has already explained, the challenge is not really with the change in the global mean sea level rise. It's the change in the local sea level rise that is important. And on top of that, there are a number of amplifiers that bring us more sea height as a result of various natural phenomena taking place that could be taking place at any given time. So if we think about the baseline rise in sea level, we need to add to that sea level related natural events such as extreme rainfall and storm surges that could add considerable height to the sea level at only one particular time in any one particular location. So a storm surge would bring us larger waves, which would have considerably more energy and would have the potential to ingress further inland. And of course, any rise in the base sea level provides a potential for a much further inland ingress of those higher waves. And if that was combined with an extreme rainfall event in a storm, we might expect a lot of runoff. And we might also expect the local rivers to swell, local drainage channels to swell, and this could exacerbate the effect of the localized rise in sea level and the impact of the storm. So a triple whammy, if you like, a worst case scenario would be one combining an extreme high tide with a storm surge and a heavy rainfall event. And as you can see from the pictures here, this is the sort of natural event that happened with Hurricane Katrina. So what can we do, and what are our options to adapt to such a challenge? Well, there are options around engineering, and of course, some of these have economic implications, and there are social science implications that we also need to take into account. So as engineers, we would typically look to provide some sort of infrastructure solution, and we might think about building barriers such as the Thames Barrier in the picture, or higher walls around our communities and engineered infrastructure. The challenge here, of course, is that with the scale of the infrastructure and the scale of the urban landscape to be protected in the future, and the economics of protecting to that scale may mean that this is in some cases not really a tenable or viable solution. So we might need to think of other ways of approaching this challenge. Of course, we could put individual buildings and pieces of infrastructure on stilts, as happens already in certain parts of the world. So in the picture here, you can see a house in Louisiana that's been risen on stilts to avoid regular flooding from ingress of seawater due to sea level rise impacts already taking place in that region. But of course, then we have to think about putting the services that service the building, the electrical power and the water services, the other utilities, gas, etc., into the building in a different way. So there are challenges associated with that, and of course this may not be a viable option for large-scale pieces of infrastructure. Another option is that we could create space for the water to move into during times of severe coastal flooding as a result of either the base tide level increase or the increase of that height further by the natural phenomena I discussed earlier. And here in this picture, you see a picture of a city area that's been set aside for ingress of water at times of flooding. Of course, you could do the same with the lower floors of buildings. Or, of course, ultimately, we could abandon places altogether and retreat to higher ground. But there are significant psychological and social effects in doing that, as well as economic effects. And those challenges have already been experienced in the wake of Superstorm Sandy on Staten Island, and again in places like Louisiana, where communities are having to abandon and retreat to higher ground. And the photo there shows the older St. Charles in Louisiana. So turning now to the specific findings of the project. So we looked at two areas from the Institution of Mechanical Engineers perspective. The two areas that we're most interested in is building services and industrial infrastructure. So looking at building services, first, I've already mentioned that services such as electrical power, water and gas utilities, and the provision of drainage, sewage, district heating, internet and telecoms, etc., all are potentially substantially affected by flooding. And as sea levels rise and coastal floodings impacts potentially increase, then communities large and small worldwide, from villages to mega cities, will be affected. So the question is what we do with underground services and those on the lower levels of buildings, and in particular what we do to mitigate and adapt to the challenge of corrosive seawater and moisture. So corrosive seawater is a particular problem. It's possible to protect against a non-corrosive water, but of course seawater is a particular challenge for engineering. And in some cases, this might be involve repairing and replacing and renewing systems, but that can be expensive and disruptive post-flood event. And in some cases, we're already finding in areas of the world that are already suffering from sea level rise that this work doesn't necessarily get done, and it can lead to blighted areas with no services at all. So turning to my particular area of interest, which is industrial infrastructure, as chair of the Process Industries Division Board, we're interested in oil and gas plants, chemical processing plants, pharmaceutical manufacturing, food processing, bulk materials handling, water and wastewater treatment, power generation in many forms, and energy sourcing in the broadest context. And of course, all this infrastructure underpins the economic well-being of local places as well as nations as a whole. And so it's incredibly important that we do think about how we, in the future, how we approach the potential challenge of increased coastal flooding from sea level rise in areas where these infrastructures are in place. And much of this infrastructure tends to be located on the coast or on tidal estuaries, both for historical but also for very practical technical reasons of needing import and export facilities for the feedstock that's coming into the plant, or indeed the products that are leaving the plant. And what we found across the areas that we looked at, both in the UK and overseas, that progress on implementing for coastal flooding adaptation is extremely limited at the moment, with very little understanding of the potential for sea level rise this century, and indeed the sort of challenge that we've been laying out in this webinar has in many cases not been taken into account. And so the challenge with this sort of industrial plant really lies around some very detailed technical issues which we consider in the report, where we're thinking about things like the overloading of surface wastewater systems, restricted access to the plants, things like water ingress into motors, pumps, and other electrical equipment, and disruption to the services such as power, gas, internet, telephone, which could lead to temporary or indeed ultimately permanent shutdown of the plants. Of course, there's much feedstock associated with these plants, and moisture damage to this feedstock on dry stores, and indeed the pipe work and services that feed those stores can be challenging. Hydraulic uplift of submerged pipelines and vessels and foundations is another area that we considered, and indeed many of these sites have areas of land that has been previously contaminated, and local ground and water contamination as a result of flooding is a very real possibility. So how can we design in such an uncertain world? And indeed, our recently published report attempts to begin answering that question for the engineering community. So the starting point for an engineer that's beginning the design of a new build or retrofit is typically to consider the requirements of the applicable design code, guide, or regulation or standard in the first instance that applies to the type of design they're doing. This might typically be the relevant Euro codes, such as structural Euro codes, and other standards available through the BSI. So on this slide, I show a range of standards that are in the public domain at the moment for how to address the issue of adaptation to climate change. So the recently published BSI standard EN ISO 1490, which is looking at adaptation to climate change and considers the principles, requirements, and guidelines, attempts to provide a general overarching standard that leads to a framework for organizations to use when considering climate change impacts and effective adaptation options, regardless of the sector that they're involved in. BSI are currently developing additional standards and detailed methodologies for very specific areas. So they're developing ISO 1491, that will look at vulnerability, impacts, and risk assessment. And they're also developing ISO TS 1490, which will consider greenhouse gas management related activities, and within that, the requirement and guidance of adaptation planning for such organizations as local governments and communities. But although these are a great starting point, these ISOs are not design codes specifically, or engineering guides, or indeed regulatory requirements. And direction for engineers on the next technical step beyond understanding the overall potential impacts and making adaptation plans is not really available to us at the moment. So CEN and CENELEC, which are the official European standards bodies, have begun working with the European Commission to modify certain infrastructure standards to cater for adapting to future climate change under the EC mandate M515. And within the UK, BSI is now planning a standard on adaptation pathways, which is a concept referred to in ISO 1490, which would help fill the gap in some of the detailed guidance between 1490 and design codes. But the challenge for us is that these general standards, although extremely useful and very valuable, are not specifically focused on sea level per se. And organizations can and really do and should do draft their own adaptation and resilience requirements. So the energy sector already does this in relation to ETR 138, which is a guide to flood proofing of substations, for example. To help organizations do this and meet the challenge, the engineering profession needs to develop simple design guidance that considers the possibilities of the dynamic and potentially sudden rises in relative sea level, such as those that were referred to by John earlier in this talk. This work should evaluate proposed design approaches and methodologies through the lens of a worst-case scenario, exploring options to accommodate such a scenario. But the question, of course, then that raises is what should that worst-case scenario be, and where should we start? So we need a simple approach to begin to offer guidance for engineers as to how to start to design for this challenge of uncertain sea level rise. So of course, John gave us a simple starting point, which he referred to as the England 9-box matrix, and I've reproduced that matrix in this slide. And here we can lay out the risk sensitivity of a particular project, so whether it's low, medium, or high. So, for example, a low project might be a local sports facility, and a high-risk project with high sensitivity might be a nuclear power plant, for example. And then we can consider that against a range of operational lifetimes to determine what sort of base global mean sea level rise we might expect in that time frame and need to design for. So, of course, we need to transition that as engineers into some sort of design height for us for our design processes and methodologies. So in the next box below, I've provided a worked example of how we might build upon the England 9-box matrix. So the first thing that we need to do is we need to work out the local mean relative sea level rise at a given particular location. So we need to do a adjustment of the global mean sea level rise, and you can see in this example that I've reduced the local mean relative sea level to a value of 500 relative to the global mean sea level for that case of 600 millimeters. And on top of this, we need to add an extreme high tide because we only have a mean relative sea level at the moment. And then we need to add on those natural effects I mentioned earlier of a storm surge impact or a potential runoff and river flooding impact. And you can see some numbers that I've used for those sort of natural events in the table. So this gives us a short-term flooding total, which we can add to the local mean relative sea level rise and end up with a design planning height for maximum floodwater for some initial calculations in the short term, while the engineering community and our colleagues develop a much more sophisticated approach in the longer term. So, of course, in addition to these, having determined the maximum total height of water we're likely to experience at any one location, we need to think about the sort of solutions that we might put forward to some of the technical challenges that I raised a few slides back. And in the report that we've recently published, we look at some 20 challenges of that nature, some significant technical challenges that we need to consider adaptive engineering solutions to, and indeed provide a number of thoughts on those solutions. So some examples of how we might meet those challenges. Of course, in the much longer term, the engineering community needs to work towards more as a result of techno-economics associated with the uncertainty of these sea level rises towards more sophisticated methods and sophisticated approaches, such as potentially development of adaptation pathways approaches, probabilistic modeling methodologies, and adaptive ready approaches that enable us to future-proof design. So we may be heading somewhere towards the sort of design methodologies that we use with in other highly uncertain environments. So to summarize, the key takeaways that I think we need to note from today is that as John has explained, the world is warming and glaciers and ice sheets are melting and the seas are indeed rising, and there's considerable uncertainty about how much rise will take place at any given location at any given time. And of course, the big challenge for us as engineers is that our engineering design approaches are based on historical data that really no longer applies for designing forward over the coming decades and indeed into the next century. So we need some new design approaches, and we need some new design methodologies, and we need to consider how designs can be adapted for for the challenge of an uncertain sea level rise. And so at its most fundamental level, we as a profession need to develop a range of new design guidance, methodologies and tools based on approaches that enable us to consider the techno-economics of our projects and provide various adaptive pathways depending on risk and change in projected sea level rise. And we need to develop probabilistic methods and ways that we can deliver adaptive capacity to our designs. So our outcomes need to be adaptive ready, they need to be future-proof, and they need to apply to new builds and retrofits. I hope you found today's webinar of interest, and if you want further information, I'd direct you to the report that we've recently published. Thank you.
Well, thank you, John, and thank you, Tim. They were excellent presentations, give us a good overview of this topic. Now, we've got some questions have come in, and of course, we've got time. If you want to put some more questions into the question box, please do, but I'm going to proceed straight away to start answering some of these questions. I think, John, the first question over to you is, could you explain a little bit more about the 9-box matrix which you raised and its concept to safety factors and risks?
Sure. You know, given the uncertainty about how Antarctica and Greenland will melt, there are all these different scenarios. The IPCC runs 4 different scenarios typically. And engineers, I've finally figured out by working with IMechE and others, you want something much more specific. You don't want 4 scenarios to design for without knowing which one might happen. And the truth is the glaciologists can't tell you which one will happen because we don't know how warm the world will be. But it is something more fundamental. Knowing or believing that sea level will be 37 centimeters by a certain date isn't really the design criteria, I figured out. The truth is we always have a margin of safety, whether it be steel trusses or the amount of concrete or density. You always have a margin of safety in your design, right, against the force that you're designing against. So we're really asking the wrong question typically of how high the water will be, particularly given the uncertainty. The fact is, what engineers need is some fairly simple guidelines to say, to be safe, we should be building 1 meter or 2 meters above sea level, in effect, on top of the existing maximum flood heights from storms and extreme tides. So it's really just to oversimplify, in effect, to say, let's think out 30 years, 50 years, and 100 years, which are 3 good building parameters if you want to think about the longevity of infrastructure and buildings. And then think about low risk, medium risk, and high risk. Because as I like to say, it's if you're designing a soccer field, it's a bit different than a nuclear power plant. And, so that's really the concept there. 3 columns and 3 rows.
John, that's very helpful, and that is in our report, by the way. Tim, you mentioned the idea of adaptation ready. What does that actually mean to us engineers?
Yeah, thank you very much, Frank. I think adaptive ready is a concept where really we're responding to the techno-economics of the challenge that we face. So let me give you a good example. So if we were thinking about building a seawall to protect some industrial infrastructure, the first question is how high do we build that seawall? And of course, there are economic implications in making that decision. And if we build the seawall too high, the engineering community and indeed those that are funding the seawall extension will begin to get concerned about the fact that we've spent money on a facility or a wall that we don't really need in the longer term. So adaptive ready is where we do a certain amount of the basic work to ensure that we can extend or build upon the initial design. So with a seawall, for example, we'd ensure that the foundations were strong enough to take a higher wall, the increased mass of a higher wall, and that we put all the foundation bars and the reinforcement in the wall in such a way that we could build higher at a later date. So Adaptive Ready is ensuring that in your design you're accounting for a later extension or increase in robustness of the design that you've produced.
Good, thank you, Tim. Now, questions come in. Should we revisit some of the previous proposed mega projects, such as installing a massive pipeline from the Mediterranean to the Dead Sea, which would help reduce sea levels, obviously by draining water in that direction, and produce huge quantities of hydroelectric power? So, John, is this one for you? These kind of projects?
I can't speak about the hydroelectric power, but just in terms of thinking of the Dead Sea as a place to put the excess seawater, if you just look at the scale of the world's oceans, the global oceans, of course, which are connected to the Mediterranean, and then the smallness of the Dead Sea in comparison, from a water level standpoint, that's not going to work. We have to do the numbers.
Thank you. You mentioned earlier about the fact that rising sea levels is related to seawater temperature. What is the rate of sea level rise per degree C, say, in the context of the warming climate?
Sure. So in the last century, the global oceans have warmed approximately a degree Celsius, and the contribution by thermal expansion, not the part that comes from melting the ice sheets on land, but just the thermal expansion of seawater is about 8 to 10 centimeters. So that's probably a good rule of thumb.
Another question that's come in is, in the future, do you think that there is a possibility of using offshore oil rig platform technology, like a design basically, to erect infrastructures at high risk levels where sea levels might rise, and that's a substitution for traditional construction and infrastructure? In other words, raising things up on these mega structures that we already have available.
I think in some places there will be elevated platforms, and perhaps structures like the oil field structures, is a good technology or approach. Again, when you think about the size of the city of Mumbai or Calcutta or Jakarta or even Miami with 4 million people, I guess it's an interesting thought exercise, an engineering challenge. We're talking about huge areas, though, in terms of the areas that are going to be submerged. So I think in isolated places, perhaps to establish a sustainable port city, a port facility in an area that's sinking or very low elevation, that might be very functional.
Good. Okay. Thank you, John. Now, another question. If sea level rises cannot be stopped for centuries, should we spend less effort on trying to stop that happening and more on adapting? I think, Tim, it's one for you.
Yeah, so I think there's some conceptual things we need to make clear here as part of this answer. So one of the things that John mentioned as part of his presentation was the fact that if we reducing greenhouse gas emissions to zero immediately would have no significant effect on the sea level rise that we're going to experience over the coming decades, and indeed into the next century. It has an impact potentially on the rate at which the sea level will change, but ultimately we can't stop sea level rise because we've already warmed the oceans, the glaciers are already melting, and the thermal momentum, if you like, that's established is unstoppable. So in terms of reducing greenhouse gases, of course, we still need to do that. But we certainly do need to start investing significant effort, both in terms of thinking, policy development, innovation around finance, and environments such as the regulatory environment, to start to produce adaptation strategies that will help us build a resilient infrastructure and resilient communities to meet this challenge that John has laid out this morning.
In fact, Tim, just adding on that we talk about climate change as a problem or the problem, and it really is three problems. We have to reduce the warming, the issues dealing with the energy production of carbon dioxide, which is a warming gas, as we know, been demonstrated here in 1859 by Sir John Tyndall. We have to be more resilient to these extreme events, everything from fires to high temperature to flooding. And then we have to adapt to changes in baseline, like sea level. And so I like to say that, well, people, if you say that we're going to deal with the problem of climate change, it suggests there's one problem and one solution. And in fact, we have to at least think of the three different aspects of it.
Thank you, John. I suppose related to that is a question some people might ask, is if we were to get to net zero carbon as soon as possible, like tomorrow or maybe by 2038, as the IPCC is recommending, would that halt sea level rises?
Yeah, no, great question, and unfortunately the answer is very sobering, because if we went to zero emissions today, let alone 2030, the truth is there's enough heat in the ocean that we're going to have meters of sea level rise. We can slow it, we can no longer stop it.
Okay, following on from adaptation, we've got a question here which is getting quite specific actually. Somebody sent us an image, I haven't got that image up actually, but the question is that in Norfolk, the gas terminal people are using seascaping to combat the rise in sea levels and repel erosion. Is this putting a plaster over the problem? Is it a temporary measure? Do the owners pack up and find a higher ground to go to? Or is this a case for a seawall? Yeah, quite a lot of variation there. So, Tim, what do you think?
So actually we discussed the Beckton and Walcott example in the report, and sandscaping is one approach to providing a softer barrier to the impact of, or to the risk of coastal flooding from increased sea level. It's part of a suite of approaches, and I think we have to take each case on an individual case and consider all possible adaptation strategies for the given case. And I think in Beckton and Walcott, the geomorphology of the coast and the mechanisms involved in sand movement along the coast, etc., meant that type of approach was suitable. So I think it's very much a question of taking each individual challenge on an individual basis.
Thank you, Tim. John, could you say how much of the additional CO2 in the atmosphere is simply a result of the increased temperature of the sea, the atmosphere, increased practical pressures? If this is significant, is this yet another vicious circle?
Yeah, great question. Effectively, it's asking how much of the current situation is natural and how much is human caused. And for those who want to see a slide of mine that might help on this, if you submit just an email to slides@johnenglander.net, you'll get a set of graphic slides. The point is that the ice age cycles have been going on for 3 million years. It's roughly a 100,000-year cycle up and down. We would have been entering the cooling phase by nature. We're entering a super warming phase right now. So effectively, we are just accelerating sea level or the warming and the sea level rise. We've broken out of the natural ice age cycles that's persisted for 2.5 million years. We're in new territory. We're going up when we should be going down.
Thank you, John. And I'm afraid we're moving on time. I'll have to halt the questions there. I'd like to thank everybody who did put in questions, and I'm afraid we didn't manage to answer them all in the time available, but I'd particularly like to thank all our participants and attendees, and particularly our two presenters, John Englander and Tim Fox. This webinar provides an excellent insight into this important topic, and we will make the recorded webinar available to anyone who wants to attend later by placing it on our website. And I'd ask you to recommend it to your friends, colleagues, and of course any schools and colleges who want to use it. It's got some important information on it. And finally, please download our report from the website. We had a press release this morning. The report on rising sea levels is now available on the IMechE website. And finally, thank you all very much for attending.
Thank you, Frank.
Thank you.
Thank you, Frank.